Hello, class. I'm John Polvey.
I'm Krishnan.
I'm Michael Lawrence.
And I'm Meghana Bellari, and we'll be discussing materials used in maxillofacial prosthetics. Maxillofacial prosthetics are a type of prosthetic used for replacing missing areas of bone or tissue in the face or body, and can also be used for cosmetic purposes. There are two types, extraoral and intraoral, and silicone and titanium are two materials that can be used for scaffolding, such as silicone scaffolding and titanium mesh.
The silicone we're focusing on in this presentation is high temperature vulcanized silicone, and this particular one is a copolymer with the monomers in the bottom left corner, and it undergoes vulcanization by a free radical addition, forms crosslinks to make a more resilient three-dimensional structure.
Titanium is used in a multitude of medical implants, but we are focusing on titanium 6 aluminum 4 vanadium ELI, also known as ASTM F136 for its biocompatibility and strength. This extra low interstitial ELI is a factor that reduces the oxygen, iron, and nitrogen content in our alloy, but this also helps to improve ductility and fracture toughness. These two materials are strikingly different because one is a polymer while the other is metal.
Silicone in general tends to be an opaque white elastomer capable of stretching over 4 times its normal length. Its edge strength is where it lacks and tends to be weaker though. Density tends to be on the lower end at about 1.1 grams per cubic centimeter, and compared to most other polymers, silicone is quite heat resistant, with a melting point usually within the 180 to 220 degrees Celsius range. But that level of heat resistance is nothing compared to that of metals like titanium. Silicone is also a poor electrical conductor as well.
Titanium 6 aluminum 4 vanadium ELI is a gray alloy metal, specifically an alpha-beta alloy, where the alpha phase is aluminum stabilized in HCP crystal structure, and the beta phase is vanadium stabilized in a BCC structure. Compared to silicone, titanium has a higher density of 4.43 grams per cubic centimeter and has a much higher melting point of 1,674 degrees Celsius. And similar to silicone, it is also a poor electrical conductor.
So in terms of mechanical properties, silicone exhibits a very typical stress-strain curve for any polymer. You can see it has a yield strength of around 2.5 megapascals and an ultimate tensile strength of up to around 5 megapascals, depending on how it's composed. And one interesting thing about the silicone is the endurance limit. With the endurance limit means it can undergo that amount of stress as many times as it can without exhibiting any fatigue. And so it works really well to hold its shape over time under small but continuous stresses.
The stress strain curve for titanium shows titanium treated in various ways. AB stands for as built, SR is for stress relieving, and HT stands for heat treated in temperature Celsius following. So heat treatment of titanium treats the metal at higher temperatures, which changes the crystal structure, and then slowly cooling them down to room temperature in a process called annealing. This raises the ductility of titanium. However, it also lowers the mechanical strength and the yield stress and the ultimate tensile stress.
And the notable difference between silicon and titanium is that silicon is significantly more ductile and titanium is significantly more strong and more tough. The Young's modulus for titanium is a lot higher than that of silicon, but silicon can be stretched a lot more, where titanium breaks faster.
In regards to degradation, silicone is susceptible to hydrolysis and attacks by its acids and bases. Silicone plastics and rubbers tend to swell when exposed to hydrocarbons, and because of their relatively weak strength, degrade as a result. Typically, the expected half-life of silicone components in maxillofacial prosthetics is about 6 months due to physical wear and loss of coloration from the body and weathering that naturally occurs. Non-vulcanized, lower molecular weight silicone prosthetics tend to be better resisting degradation from areas such as heat, water, and oxidation.
Titanium undergoes a uniform corrosion when it's in an acidic environment, which dissolves its oxide layer, causing the titanium oxide to undergo reduction. Reduction produces titanium plus 4 ions that hydrolyze and form insoluble titanium dioxide. When there's a lack of oxygen, titanium hydrides form. Titanium doesn't really have a timescale for degradation because it is so highly resistant to corrosion because of its oxide layer that forms around its surface when it's exposed to air.
Like titanium, silicone is quite resistant to degradation, but components tend to get replaced periodically to maintain a high level of performance and to minimize already rare occurrences of degraded material associated toxicity. Unlike titanium, silicone does not evenly degrade due to its amorphous nature.
So the surface properties of silicon that are important is it's pretty biocompatible. It has outstanding temperature and oxidative stability. It has good low temperature flexibility, and it has high resistance to weathering and a lot of chemicals. Silicon also has low surface tension and is capable of wetting most surfaces.
Titanium also exhibits biocompatibility due to its low electrical conductivity and the same oxide layer which prevents corrosion. This oxide layer also allows titanium to fuse with bone in this process called osseogeneration integration. Both of these materials exhibit biocompatible properties and resistance to corrosion.
The main disadvantages of titanium is that it's costly and its gray color can sometimes be seen under skin. For titanium mesh specifically, it's difficult for surgeons and for regeneration therapy of small or medium-sized defects. In addition, microbial contamination of the healing site can easily occur when titanium mesh with large and many pores is bent or cut. Some future directions to resolve these issues are to design titanium so that it can be fixed directly onto the implant for an easier surgery process, and for the titanium mesh to be less porous and for its pores to be micro-sized to prevent microbial contamination.
In regards to silicone, the main challenge is pigmenting the material and processing it due to its relatively light nature and low strength, which in itself is another problem. Its low strength is noticeably lower than that of other materials such as titanium. Future directions that can be taken to improve the design include treating the silicone with surface-treated silica filler, which increases the surface area and decreases the particle size, which enhances the physical and mechanical properties all in all. Nanosilica powder in particular in recent studies has been promising as it further improves mechanical and physical properties with its increased surface area and even smaller particle size. Hollow microspheres also improve the particle performance in testing and can be of promise in the future. Shown here is a graph that shows the dramatic increase by multiple magnitudes of resistance carried by silicone with the increase of filler added to it. Thank you for listening to our presentation, and thank you for a great quarter.